All right, you guys. Well, I haven't done this before, so we're just going to give this a shot. All right. So today we have 3.1 exponential functions and their graphs. I'm also going to include 3.2 in this video, and if I have enough time, 3.3 as well. All right. So these are the notes that you'll have to take. Again, there are just some definitions that I'll mention. You can just pause the video when I mention them and jot those down. And then we'll go through everything else and just see how this goes, all right? Yeah, let's get started. So 3.1, exponential functions and their graphs. All right, first thing, exponential function. That would be in the form f of x equals a to the power of x. A has to be greater than 0, a cannot be equal to 1, and x can be any real number. All right, so that's a quick definition. Example 1, we're going to use a calculator to evaluate each function at the indicated value of x. So letter A, we have f of x equals 2 to the power of x. Super simple. All we're going to be doing is plugging in the value of x that they give us. So letter A, maybe I'll do that over here actually. A little hard to see over there. So letter A, we have f of negative 3.1 equals 2 to the power of negative 3.1. All right, then all we have to do, just type this into our calculator real quick. All right. When we're plugging this into our calculator, we just do 2 to the power. So again, that's this caret button. 2 to the power of negative 3.1. If you're not so sure that it's going to type in correctly, put that power in parentheses. So negative 3.1 in parentheses. All right. And we get f of negative 3.1 is approximately 0.117. All right. Now, letter B. This is going to work the exact same way. And I'm just going to write, well, we'll go through each one at a time. So f of, this time we're plugging in pi, f of pi equals 2 to the power of negative pi. Again, type that into our calculator, 2 to the power of negative pi. Even if I type that in without parentheses, this one is going to work fine. All right, so we would get 0.113. Letter C, f of 3 halves equals 0.6 to the power of 3 halves. Now this one, we do have to type this into our calculator with parentheses. So when we type this in, we take 0.6 to the power, and then that 3 halves has to be in parentheses. So 3 halves in parentheses, and then press enter. There you have it, 0.465. Letter D, f of 12 equals 1.05 to the power of 2 times 12. All right, again, this is going to be something where we are going to want to type this into our calculator with parentheses, or if you don't want to type it in with parentheses, you could do 1.05 to the power of 24. That is 2 times 12. So 1.05 to the power, and then parentheses 2 times 12. We get approximately 3.225. Example 1, all done. Example 2, graphs. So we have to sketch the graphs of f of x equals 2 to the power of x and g of x equals 4 to the power of x. So I have to go get some graph paper here real quick, and then we will just go ahead and graph this. So we're just going to label this here example 2. All right, and we have f of x equals 2 to the power of x, and g of x equals 4 to the power of x. And again, we want to have this on the same coordinate plane. So first thing that we want to do, label our graph x, y, 1, 2, 3, 1, 2, 3. And actually, I might actually change my y scale just a little bit, and you'll see why here in just a second. So we're gonna go by 4s, 4, 8, 12, 16, and I'll just keep going, 20, 24, 28, 32, 36. And then y, or negative x is -1, -2, -3, -4, -8, -16, yada, yada, yada. We won't be as interested in our negative y's. All right, so now all we're gonna do is just type this into our calculator, get some good answers. Now some of these you probably won't even need to type into your calculator. You just plug in numbers for x. So if we say, let's plug in 0 for x. 2 to the power of 0 is 1. So put our point at 0, 1. When we plug in 1, we get 2 to the power of 1, which is 2. When we plug in 2, we get 2 squared, which is 4. When we plug in 3, 2 cubed is 8. When we plug in 4, 2 to the 4th is 16. When we plug in 5, 2 to the 5th is 32. All right. You probably notice that as we get closer to the x-axis, we approach 0. This will actually never be 0, and we can check that. All right. Just for the sake of seeing how close it gets, if we type in like 2 to the -5th power, we get 0.03125, so it's going to get closer and closer to 0. If we want to put a couple of definite negative points on here, we can plug in 2 to the -1, we get 0.5, so exactly 1/2. If we plug in 2 to the -2 power, that would give us 0.25 or 1/4. All right. And then we can just go ahead and connect these dots and have our line extend pretty close to the y or x-axis here. Ooh, that did not turn out so good. All right, right at an awkward angle here. There we go, that's a little bit better. All right, so that is f of x, and we're gonna wanna label that f of x here. All right, that way we have this graph labeled. Now g of x, when we plug in 1, we get 4 to the power of 1, 4 to the power of 0, sorry. 4 to the power of 0 is 1. 4 to the power of 1 is 4. 4 squared is 16. 4 cubed is 64, which is not on our graph. All right, so again, if we wanted some other points here, we just plug in -1, but again, it's gonna have the same kind of idea that g of x is gonna have here. All right, so this one just goes up quite a bit steeper. This next point is gonna be 64, so we're just gonna be in between 2 and 3 here, and it shoots up. All right, so that's example 2. Both of those graphs are on the same plane. Oh, again, make sure to label your graph g of x. All right, so now we have them both labeled. That is properly labeled. Example 3, same kind of deal, except now we have to graph the each of these two graphs, which are just slightly different. F, so capital F of x equals 2 to the power of -x. G of x equals 4 to the power of -x. All right, we're gonna see similar graphs. The only difference in this one, and you'll kind of see this when it happens, is that these graphs are, instead of going up, they're going to go downwards. We'll use the same scale for our y, 4, 8, 12, 16, 20, 24, 28, 32, 36, -1, -2, -3, -1, -2, -3. All right. And then we're just going to plug in some values here, okay? So first we'll just go ahead and go 2 to the power of, and then here we have -x, so we're going to have negative, and let's say we're going to plug in -4 first. So 2 to the power of -4, or 2 to the power of +4, which would be 16. If we did 2 to the power of -5, that'd be 32. -3 would be 8. -2 would be 4. -1 would be 2. And 0 would, as always, be 1. All right, so you can kind of see what happens with this graph here. Instead of going up as we go to the right, this graph goes down as we move to the right. So that negative exponent means that it decreases from left to right. When we have g of x, if we were to plug in -3, we would get 4, and then 4 to the power of -3, which would be 4 to the third, which would be 64. Again, not on a graph. So if we plug in 2 or -2 instead, we get 4 to the power of 2, which is 16. 4 to the power of -1 would be 4 to the power of 1, or 4. When we plug in 0, we get 1. And then again, this one gets increasingly close to the x-axis. So same kind of deal here, except the opposite direction. Oh, that one took a turn for the worst. All right, so again, label this f of x, label this g of x. And then we have both of those graphs, all right? So on now to this next portion. So build understanding, there's just some information about exponential functions. So they include all of this here. Not really stuff that you necessarily have to memorize, but you do have to, or you are going to have to be able to find it just by looking at the picture. So domain, range, intercepts. So here are just a couple examples. So example 4. Each graph shown below is a transformation of the graph of f of x equals 3 to the power of x. So transformations again. Letter A, because g of x equals 3 to the power of x plus 1. So this would be that part where when we think of it, this is in parentheses. So we've got addition in parentheses, in quotes, all right? That means that we have a horizontal translation, all right? So it's plus 1, it's to the left. So we have a translation 1 unit to the left. This one here, we've got 3 to the power of x minus 2. All right, this time this -2, this is just applied to our whole function. All right, so that means that we move down to vertical translation, down to. Letter C, we have k of x equals -3 to the power of x. All right, again, that negative sign, that means that we've got a reflection. Since it's not in parentheses, that would be a reflection in the x-axis, so over the x-axis. And letter D, because j of x equals 3 to the power of -x, so now we can see that negative sign up there. Again, think of that as being in parentheses, right? That's where our x is at. So since that's in parentheses, it's a reflection in the y-axis. If we were to look at the graphs of each of these functions, letter A would be right up here. Letter B would be right here. Letter C, and letter D. All right, so you can see this one and move to the left one. This was our original, move to the left one. This was our original, moved down to. This was our original, and it reflected over the x-axis, so now it's upside down. And then letter D, this was our original. It reflected over the y-axis, so 3 to the -x. Similar to example 3, we could see that that one went down as we moved from left to right. All right, so just some transformations, and next we are going to, we'll do a couple of examples here. So just a couple examples of transformations here. We have g of x equals 4 to the power of x minus 2 right here. All right, so again, think of this as being in parentheses. This would be our horizontal translation, right 2. Letter B, we have h of x equals 4 to the power of x plus 3. This would be our vertical translation, up 3. Letter C, we have 4 to the -x minus 3. So in this case, we have two different transformations. This -3, that would be our vertical translation. This time, down 3. And then we have this -x in our power. That would be our reflection. Since it's in parentheses, this is over the y-axis. So over the y-axis. And again, you can use the terms reflecting in the y-axis or about the y-axis. I prefer to use the term over the y-axis, reflecting over the y-axis. All right, so next piece here, the natural base E, they give you just a little bit of information. E, again, is an actual number. This is not a variable. E is the number 2.71828128, and then that continues. So this is a number. This is not a variable. So a graph is going to be an exponential graph, but it's going to be 2.718 to whatever power that we are using. So example 5, evaluate the expression 1 plus 1 over x to the power of x for several large values of x to see that the values approach e to the e is approximately 2.71828 as x increases without bound. So what we want to do for this one is we're just going to plug in some values for x, and we're going to make them increasingly larger. So we'll just start with 1. So when x equals 1, we have 1 plus 1 over 1 to the power of 1. I'll give you a hint. This is 1 plus 1, which is 2. 2 to the power of 1 is 2. All right. If we plug in, let's say 10, x equals 10, we'd have 1 plus 1/10 to the power of 10. If we were to plug that in, that's 1.1 to the power of 10. This is the number that we get, 2.59. We'll go 3 decimals, I suppose, 2.594. All right. So you can already start to see that we're getting closer to that value. Now let's just go with a larger number. X equals 100. So we have 1 plus 1 over 100 to the power of 100. All right. So this time we have 1.01 to the power of 100, 2.704. So this is approximately 2.705. All right. So again, we can see that we're getting closer. Now let's try just one more time. X equals 1,000. So we have 1 plus 1 over 1,000 to the power of 1,000. So this time we have 1.001 to the power of 1,000. We get x is approximately, or not x, we get our answer is approximately 2.717. All right, I'm going to stop it there, but you can see it getting extremely close. Maybe I'll just try one more example, but I'm not going to write it down. 1.000001 to the power of, and this would be 1, 2, 3, 4, 5, 6, 7. All right, so 1, 2, 3, 4, 5, 6, 7. All right, so 7 zeros there. So 2.718281, and then here you can see that's some more variability. But when we increase it that much, we can see that pattern. It does approach 2.718 repeating. All right, so that's the value for E. E, when you plug in infinitely large numbers for x, it gets closer and closer to 2.718. All right. The checkpoint for this one, pretty similar. You would just plug some numbers in for x, see that it approaches this number, 7.389, etc. Example 6, use a calculator to evaluate the function. Again, this is fairly easy here. So f of x equals e to the power of x. All we're doing is plugging in the values that they give us. F of -2 equals e to the -2, which is approximately our button for e here. You could either use this button here, this is e to the power of x, or you could use e here. I generally use just e, but you'll get the same thing either way. So e to the -2 is approximately 0.135. Letter B, we have f of 0.25 equals e to the 0.25. Again, I'm going to type this in. Second e to the power e to the power of 0.25, 1.284, so approximately 1.284. Letter C, we've got f of -0.4 equals e to -0.4, which is approximately e to the -0.4, 0.670. Letter D, f of 2/3 equals e to the 2/3. And again, this is going to be one of those examples where we do have to have that that power in parentheses. So e to the power of 2/3, 2/3 has to be in parentheses. 1.948. All right. Example 7, sketch the graphs of f of x equals 2e to the 0.24x and g of x equals 1/2 e to the negative 0.58x. So again, I'll write these over here. Example 7, we have f of x equals 2e to the 0.24x, and then g of x equals 1/2 e to the negative 0.58x. What I'm going to do for this one here is I'm just going to type this into my calculator into the y equals section, and then we're just going to go ahead and see what we end up with. So we'll go to y equals, and then we've got 2e to the power of 0.24x, and I'm going to put this in parentheses actually, so that 0.24x in parentheses. And then we can also type in this 1/2, so 1/2 e to the power of negative 0.58x, close that parentheses. And then you can either graph it or you can use the table. I'm going to use the table for this one, so I'm going to go second table, which is right above graph. All right. And then I'm just going to type in some values. So as always, I like to go basically for our x's between -5 and +5. So we'll go -5, -4, -3, -2, -1, 0, and then 1. All right. And then we're just going to put some points on this graph here. All right. So So our y's, we'll just go by ones. That's okay. -1, -2, -3, -1, -2, -3. All right, so in this case, these are my x coordinates. These are my y's for our first equation. These are my y's for our second equation. So this is very efficient here when we do type this in. -5, about 0.6, so a little bit over half. -4, 0.76, so a little bit higher. -3, 0.97, so we're really close to 1 here. -2, 1.23, so we're a bit above there. -1, 1.5. This one might have to go down just a tad. 0, 2, 1, 2.5. So this is f of x. And now I can do the same for g of x. All right, g of x at -5 is at 9.08, so we're way up here for g of x. -4, it's at 5.08. -3, we're at 2.8. At -2, we're at 1.5. At -1, we're at 0.89. And at 0, we are at 0.5. And at 1, we are at 0.27. All right, so we've got that. Now I'm just going to go ahead and get us just a couple more values. So 2, 3, 4, and 5. All right, just a couple more things to graph. So again, for my first graph, we have 2, 3.3, or 3.2, 3, 4.1, 4, 5.2, 5, 6.6, and we'll call that good for f of x. So now we just have to connect these points here. So it kind of goes up somewhat gradually. And then again, label this f of x. Now if we look at g of x, we've got 2.15, 3.08, 4.04, 5.02, All right, so it's getting closer and closer to 0. So again, connect to these points. And label this graph g of x. So that's example 7. All right, so just sketching graphs using your table on your calculator. It's a very handy feature because you can trace it on both functions at once. All right, now just a couple things to jot down here. Our formulas for compound interest. If we have n compoundings per year, so they tell you it's annual, or they tell you it's biannual or semi-annual, or quarterly, this would be our formula. A equals P times 1 plus R over N to the power of NT. And for continuous compounding, A equals PE to the RT. Principal, P, that would be how much money that you're putting into your account initially. Annual interest rate, or R, has to be in decimal form. That's important. So if we had 17%, we would write that as 0.17. All right. Balance is A, T is years. So those are also important things to know. All right, example 8. A total of $9,000 is invested at an annual interest rate of 2.5% compounded annually. All right, keyword there, compounded annually, not continuously. So we're going to be using that equation, A equals P times 1 plus R over N to the power of NT. We have to find the balance in the account after 5 years. So we're finding the balance in the account. We're finding what A equals. So A equals, and then $9,000 is invested. That's our principal, P, times 1 plus our rate, 0.025. Again, 2.5%. You move the decimal place to the left 2 spots. And then over the number of compounds annually, which would be, in this case, 1, to the power of n times t. So our number of compoundings, 1 per year, times our time, which would be 5 years. All right. Before you type this in, I like to just simplify what I can right away. So we have 9,000 times 1 plus 0.025 divided by 1, which is just 0.025, so 1.025 to the power of 5. It just makes typing this in so much quicker. So 9,000 times 1.025 to the power of 5. So the amount in our account is approximately $10,182.67. So that's it for example 8. Example 9, a total of $12,000 is invested at an annual interest rate of 3%. So there's our interest rate. Find the balance after 4 years when the interest is first compounded quarterly, and then B, continuously. Quarterly, that means 4 times a year. All right, so letter A, same equation that we used last time. 12,000 times 1 plus our rate, 0.03, divided by the number of compoundings, which is 4, and then to the power of 4, so that's, again, our number of compoundings, times the number of years, which will also be 4. I'm just going to type this in real quick, and we will get an answer. All right, so $13,523.91. Letter B, we use the equation A equals PE to the power of RT. A little bit easier to remember, PERT. All right, so 12,000 E to the power of 0.03 times our time, which is 4. It's 12,000 E to the 0.03 times 4. That has to be in parentheses. $13,529.96. So that's it for example 9. I'm running out of time here, so I'll get back to example 10 and example 11 here in a second, and then we'll get started with 3.2 as well. Not so sure about 3.3. All right, example number 10. So we have to let Y represent a mass in grams of radioactive strontium whose half-life is about 29 years. So they're giving us a little bit of information here. Half-life is 29 years. The quantity of strontium present after T years is Y equals 10 to the power of 1/2 to the power of T divided by 29. So you can see that half-life is right here. Letter A, we have to find out what is the initial mass, so when T equals 0. So all we have to do is plug in 0 for T here. So we have Y equals 10 times 1/2 to the power of 0 divided by 29, which equals 10 times 1/2 to the power of 0. Anything to the power of 0 is 1, so we get 10 times 1, which is 10. And then we just have to label our answer. Our mass is in grams, 10 grams. All right. Letter B, we have to say how much of the initial mass is present after 80 years. All right, so for this one, what we have to do, again, T is our amount of time, so we're gonna have to plug in 80 for T. Letter B, Y equals 10 times 1/2 to the power of 80 divided by 29. And here you can plug this into your calculator. Again, you just have to be kind of careful with your parentheses. So 10 parentheses 1/2 to the power of 80 29ths in parentheses. So we get about 1.478. So approximately 1.478. And again, we want to say label here, so grams after 80 years. So you might have noticed in that first example there, what is the initial mass? When we're talking about initial, we're always talking about when T equals 0 or when X equals 0, whenever our independent variable is 0. On to example 11 here. The approximate number of fruit flies in an experimental population after T hours is given by Q of T equals 20 e to the 0.03 T, where T is greater than or equal to 0. We have to find out the initial number of fruit flies in the population. They give us this piece of information that T has to be greater than or equal to 0. That means our initial amount is going to happen again when T equals 0. So letter A, we have Q of 0 equals 20 e to the 0.03 times 0, which this again gives us a power of 0. So 20 e to the power of 0. Anything to the power of 0 is just e. So again, kind of see that that first number, that's our initial amount, 20 fruit flies. That's how many we start with. Letter B, how large is the population of fruit flies after 72 hours? Now, we just have to be careful here. Is T given in hours? It is, so we can plug this right in. Q of 72 equals 20 e to the 0.03 times 72. And we're going to get an approximation here. All right. So, again, 72 hours or 3 days. We're going to type this in. When we type this in, we have to just be careful that our power is in parentheses. So 0.03 times 72 is in parentheses. We get 173.4. So if we round to the nearest fruit fly, well, it's fine if you round up. I would probably round down in this example though, just because you can't have 0.4 of a fruit fly. So 173 fruit flies. letter C, we have to graph this equation. So we're gonna go over to our graph again. Example 11. All right, so our number of hours here goes on our X. I might, just to get a better look at this, we'll just go in 12-hour increments. So 0, 12, 24, 36, 48, 60, 72, 84, 96, 108. All right, now I'm just gonna plug in our last number of hours. So, and again, it might be easier if you go to your y equals, go to your table option. Graphing this is just gonna be a little bit quicker. So 20 e to the 0.03 x. Again, second table. All right, I'm just gonna plug each of these values in. And I'm actually gonna start with 108. That's just so I can get my highest value. So 108, 96, 84, 72, 60, 48, and 36. So you can see my highest value is 2,225.8. We will probably, that might be off of our page. We're just gonna go to 2,000 here, so 2,000. All right, that means that each of these is gonna have to go by 200, so 200, 400, 600, 800, 1,000, 1,200, 1,400, 1,600, and 1,800. All right, if you chose your scale to be a little bit differently, as long as it's showing the shape of this graph, you could change your X and your Y however you want. So I'm not too concerned. And this time we have to label our axes T and Q. All right, so at 108, it's a little bit of an overgraph at 2,225, so you can put that point down there. It's not going to be very exact. 96 is at 1978, so pretty close to 2,000. Then we have 84, which is at 1731. And then 72 is at 1483. And 60 is at 1236. And then 48 is at 989. And then 36 is at 741. And now we just need 0, 12, 24. And then we'll have it. So 0, 0. 12 is at 247. 24 is at 494. So it actually looks pretty linear here. And then we just have to connect these dots here. And we're just gonna have an arrow going to the right, not to the left, because we can't have negative time. So that is it for that one. So 20e to the 0.03t, that's kind of what it looks like. It's got a pretty slow rate there, 0.03. So it's not gonna look super crazy or super curved yet. But yeah, 0, 12, 24, 36, 48. If we look at the scatter plot here on our graph, we'll change our window to 0 to 108. X scales, we can go by 12s. Y minimum 0 to 2,000. We'll go by 200s. And I forgot to put each of these in here, so I guess we could put that 20e to the 0.03 x in here, and then I'm just gonna put in these points just so that you can see what they look like. Actually, we're just gonna look at what it looks like. Yeah, so it looks pretty linear when we do see it like this. All right, so that's it for example 11 and also 3.1. So now I'm going to start talking about 3.2, logarithmic functions and their graphs. All right, so first we have a definition. We're talking about logarithms again. Y equals log base a to the power, or log base a of x. So again, log base, or y equals log base a of x is only true if x equals a to the power of y. So x equals base of a to the power of y. So whatever your log base is, that's going to be the base of your exponent. I guess I could do a quick example here. So if we had 4 equals log base 2 of 16, right? That means that, not 2, 16 equals 2 to the power of 4. All right, so yeah, 4 equals log base 2 of 16. That means that 16 equals 2 to the power of 4, which if you check that, it is true. 2 to the 4th power is 16. All right, so that's just an example of what that's going to look like. So example number 1 here, evaluate each logarithm at the indicated value. All right, so f of 32 equals log base 2 of x. Sometimes I like to write this as y equals log base 2 of, and this should not be x anymore because we plugged in 32 for x. I like to write it this way, just so that way we can rewrite it in power form. So again, whatever this is here, this number within your log, that's equal to the base of your log to the power of the other side. So 2 to the power of y equals 32. If we think of what y has to equal, 2 to the power of something equals 32. Y is equal to 5. Letter B. We have log base 3 of x. And again, this time I'm going to use y instead. So I guess when we get to the end, we could say f of 32 equals 5. But I'm going to use y right away just because it's a little bit easier to work with. So y equals log base 3 of 1. So that means that in this case, we have, again, this number inside of your log, 1, equals your log base 3 to the power of the other side, y. Right, so 3 to the power of y equals 1. Anything to this power gives you 1. I'll let you think about what it is. It's 0. All right, so f of 1 equals 0. So when you plug in 1 to this equation, it's going to give us 0. All right, letter C. We have y equals log base 4 of 2. This time we have 2 equals our base 4 to the power of y. So 4 equals, or 4 to the power of something equals 2. All right, if we start to think about roots, this would be the square root of 4 equals 2. Now when we write the square root of a number as a power, that would be like 1/2. The cubed root would be 1/3. The fourth root would be the fourth root, so 1/4. So in this case, we'd say that f of 2 equals 1/2. This is the square root of 4. Finally, letter D. We have 1/100. Oh, sorry, wrong spot. Y equals log base 10 of 1/100. All right, let me just clean that up a bit. All right, so that means that 1 over 100 is equal to 10 to the power of something. So 10 to what power equals 100? Think of first. 10 to what power gives you 100? All right. In this case, 10 squared is 100. But since it's 1 over 100, that just means that it has to be -2. So f of 1 over 100 equals -2. All right. And if you want to, just type these into your calculator to verify. All right, so all you would do, just take 2 to the power of 5, should give you 32. And then you take 3 to the power of 0, should give you 1. 4 to the power of 1/2 should give you 2. 10 to the power of -2 should give you 1 over 100. If not, it means you probably just got your number wrong. Example 2, use a calculator to evaluate the function f of x equals log base 10 of x at each value of x. So in your calculator, when you use the log function, so if we just see log of x, that's the exact same thing as saying log base 10 of x. Your calculator has log x as a function. So all we need to do is plug this into our calculator. So letter A, we have x equals 10. So log of 10, actually, we'll say f of 10. So f of 10, just for more proper notation, just from this up here, f of x equals log base 10 of x. F of 10 equals log base 10 of 10. Again, in your calculator, that's the same thing as typing in log of 10. Right, so we're just going to jump over to our calculator. Log of 10 gives us 1. Which, if you remember from last year, log base 10 of 10, so like if you had log base 11 of 11, that's still 1. If your base matches your number, it's going to be equal to 1. We'll find out about that in a bit. Letter B, we have to find f of 1/3. So log, and I'm just going to write it as log of 1/3. I'm not going to write that log base 10 again. Log 1/3 is negative -0.477. Letter C, we have f of 2.5, which equals log base 10 of 2.5. All right, so again, f of 2.5. Let's go to our calculator. Log of 2.5, which gives us 0.398, 0.398. Finally, letter D. This time we have x equals -2. So f of -2 equals log base, or log of -2. All right. And again, we're going to see what happens here. So log of -2, and you might remember this happening here. It's going to give us a non-real answer. We can't take the log of a negative number. So f of -2 equals, it does not exist. Right, so log base 10, same thing as log on your calculator. You just plug that in. All right. Next thing, a couple of properties of logarithms. So if we have log base whatever, so a of 1, so any base log of 1 is always going to give us 0. If our base and the number within our log matches up, we're going to get 1. If log base a of a to the power of x, all right, again, I like to think of that as bringing x down here. We get x times 1, so we'd get just x. if we had log base a of x equals log base a of y, that means that x and y have to be equal. So example 3, letter A, we have to solve for x. We have log base 2 of x equals log base 2 of 3. All right, this, if you see this problem anytime, this is low-hanging fruit, right? We know that the logs are the same. That means that this has to be equal to this. X equals 3. Simple enough. B, we have log base 4 equals x. Again, when you see this, this should be just a gimme, right? Log base 4 of 4, the base and the number match up. X equals 1. Letter C, we have to simplify log base 5 of 5 to the power of x. Again, how I like to think about that is we're bringing the x down. So we'd have x times log base 5 of 5, because logs allow us to bring the power down. And then that's equal to x times 1, which is just x. So that's as simple as it gets. Letter D, we have 7 to the power of log base 7 of 14. All right, so this one, our power matches up with our log here. All right, if we go back to this page here, if we have a base that matches up with the base of this here, it's just going to be equal to whatever x is. So 7 log base 7 of 14, these two pieces cancel out. We're just left with 14. Again, you might remember that from last year. We'll just do these checkpoints here real quick. Letter A, again, low-hanging fruit. This is x equals 2. Letter B, we have 20 to the power of log base 20 of 3. That would just be equal to 3. 20, that log base 20, that cancels out. All right, all of these properties are going to be really helpful when we go through and solve some equations. So, example 4, in the same coordinate plane, we have to sketch the graph of each function by hand. So, this is 3.2. Example 4. All right, so we have f of x equals 2 to the power of x, and then we have g of x equals log base 2 of x. All right, so letter A, this one's going to be pretty easy to graph. We had an example of that last time, so I'm just going to go ahead and set this up, x and y, and 1, 2, 3, 1, 2, 3, negative 1, negative 2, negative 3, negative 1, negative 2, negative 3. All right, and then we're just plugging in values for x. If x equals negative 3, 2 to the power of negative 3 is 1/8. So 1 divided by 2 cubed, which is 1/8. 2 to the negative 2, that'd be 1 over 2 squared, or 1 over 4. 2 to the power of negative 1, that'd be 1/2, so 1 over 2 to the power of 1. 2 to the power of 0, that's just 1. 2 to the power of 1 is 2. 2 squared is 4. 2 cubed is 8. So we have this graph, and again, it gets infinitely close to the x-axis, or 0. And a nice curve, and there we have it. All right, for g of x equals log base 2 of x, if you recall what we had to do for that one, we actually had to find the inverse function. Otherwise, we weren't able to graph it. So start with saying that y equals log base 2 of x. If you recall, to find the inverse function, we switch x and y. So x equals log base 2 of y. Right? And then we solve for y. All right, in this case, you can just solve for y by writing this in exponential form. Or if we used, and I guess if we wrote it in exponential form, we take whatever's in our log, so y equals our base 2 to the power of x. If you recall from last year, when we had something like x equals log base 2 of y, to undo the log, we use the power. So we do the power of whatever the base is. So whatever our base of our log is, that's going to be the base of our powers. So we do 2 to the power of each side. And again, this cancels out this side just stays as 2x. So we get y equals 2 to the power of x. That's our equation. All right, this is the inverse function. So that means whenever we plug something in for y here, it's going to switch around. All right. So if we plug things in here, all we would have to do, and I can go ahead and plug these in just like we did for our first equation, right? Now, if we think of this, we got 1/8, 1/4, 1/2, 1, 2, 4, and 8. Now with the inverse function, all that's going to happen is x and y are going to switch. So our actual table will say inverse versus actual. Our inverse, or our actual, is just going to switch these. So x is 1/8, y is -3, x is 1/4, y is -2, 1/2, -1, 1, 0, 2, 1, 4, 2, 8, 3. All right, and then we're just going to go ahead and graph this here. So 1/8, -3, so over 1/8, down 3. Over 1/4, down 2. Oh, I'm on the wrong side. (1/2), -1, 1, 0, 2, 1, 4, 2, and 8, 3. And there we have it. So to graph the logarithm function, we always find the inverse first. And for the inverse of our log functions, that's going to be your power function, so your exponential function. All right. And just one thing to note, you'll notice that all of our x's are positive. That's because you can't plug in a negative into your log function. So that's one thing to note. You can't plug a negative into or in for x here. So all of your x's will be positive. And you can see that with our graph. Right? The asymptote is at y equals 0, or x equals 0. All right, on to example 5. Sketch the graph of the common logarithmic function f of x equals log base 10 of x by hand. This one you could plug into your calculator and just use the table function, but again, I'm going to show you how to find the inverse and then graph it that way, just as more practice here. So we have y equals log base 10 of x, switch x and y. All right, and then we want to cancel things out. In order to cancel out the log, we raise everything to the power of whatever the base is. So 10 to the power. These cancel out. We get y equals 10 to the power of x. Set up an xy table. We're just going to plug some values in for x. I like to go -3, -2, -1, 0, 1, 2, 3. All right, when we plug in -3, we get 10 cubed on the bottom, so 1 divided by 1,000, 0.001. If we plug in -2, we get 100th, 0.01. 1, 1, and then 10, and then 100, and then 1000. So this is our inverse table. And then our actual table, again, is just going to switch the x and the y. So at 0.001, we have -3. At 0.01, we have -2. At 0.1, we have -1. At 1, we have 0. At 10, we have 1. At 100, we have 2. At 1000, we have 3. All right. And I'm going to flip onto the back side. It's a little bit less bogged down here. So example 5, x, y. All right, so you can see that our x's range from 0.001 all the way to 1000. We might just go to 100 for this one, just so that we can see the shape a little bit better. So we want to get to 100 here at the end. That means we'll probably go by tens. 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. And then our y's, we can just go by ones. -1, -2, -3, 1, 2, 3, -10, -20, -30. And then we just have to plot these points. So as you can see here, our first x was 0.001, and we were at -3. So it's really close to our y-axis. 0.01 was at -2. 0.1 was at -1. And then at 1, we were at 0. At 10, we were at 1. And at 100, we were at 2. And then we just have to graph this thing. And there we have it. All right. So as you saw there, our logarithmic function, it looks like a curve. It's just going to not increase so much. So it's not exponential. It's not going to keep increasing. It's going to gradually stop increasing. All right. Now some transformations here. So again, we're looking at where the parentheses fall. So if we have log base 10 of x minus 1, x minus 1 is in parentheses. That means we have a horizontal translation, 1 unit to the right. Here, so letter B, we have h of x equals 2 plus log base 10 of x. This 2 is not in parentheses, and we're adding. That means vertical translation, in this case, 2 units up. All right, so some examples here on the checkpoint. We have -1 plus log base 10 of x. This would be a vertical translation because it's not in parentheses, down 1. Letter B, we have log base 10 of x plus 3. This would be a horizontal translation, left 3. Next thing is our natural logarithmic function. So y equals ln of x. So again, ln stands for the natural logarithm. So when I say natural logarithm, this is what I'm talking about, ln. All right, so x equals e to the power of y. Again, this can be written as logarithmic function in the form y equals ln of x. And you can also think of it as being log base e. So it's just a different name for that. Example 7, again, pretty easy. All we have to do here is plug these values in for x. So f of x equals ln x, natural log of x. So f of 2 equals natural log of 2. Type that in. You have a button here for natural log. You just type in natural log of 2, which will get 0.693. B, we have f of 0.3, which is natural log of 0.3. Again, type that in. we get negative 1.204. Letter C, we have f of negative 2. I hope for this one you can see what's going to happen right away. Natural log of negative 1. You like to get these as your answers. That one is a does not exist. Letter D, we have f of 1 plus the square root of 2. So natural log of 1 plus the square root of 2. We just have to be careful with our parentheses here. Natural log 1 plus the square root of 2. Close your parentheses so it's all the way around your 1 plus square root of 2. We get 0.881. Example 7. Properties of natural logs here. Natural log of 1 is 0 because e to the 0 is equal to 1. All right, so again, any log with 1 inside of it, it's going to give you 0. Natural log of e, so think of that again as log base e of e is equal to 1. All right, and then number 3, natural log of e to the x. Natural log cancels out e, and we get x. Similarly, e to the power of the natural log gives us just x. E to the natural power, or e to the natural log cancels out. And then finally, if natural log of x equals natural log of y, then x equals y. So example 8, use the properties of natural logarithms to rewrite each expression. All right, so letter A, we have the natural log of 1 over e. All right, so we can rewrite this right away as the natural log of e to the power of negative 1, which gives us just negative 1. All right. So sometimes rewriting that is going to be really helpful for you because then that natural log and e cancel out. Letter B, e to the natural log of 5. This one's really nice because e to the power of the natural log just cancels out. We're given 5. C, we have 4 times the natural log of 1. All right, natural log of 1, that will always give you 0. Letter D, 2 times the natural log of e. It's equal to 2 times 1, which is just 2. All right, if we look at this checkpoint here real quick, we'll do these. Natural log of e to the 1/3, that is just 1/3. Bring that 1/3 down. Letter B, 5 times the natural log of 1. Natural log of 1 is always 0, so we get 5 times 0, which is 0. C, 3/4 times natural log of e. Natural log of e is 1, so we get 3/4. And D, e to the natural log of 7. E to the natural log cancels out. We're just left with 7. Example number 9, find the domain of each function. So if you recall, the natural log or any log cannot be negative. All right, so that means whatever's inside of here has to be greater than or equal to 0. So we're just going to use that fact. F of x equals natural log of x minus 2. All right, x minus 2 has to be greater than or equal to 0. Add 2 to each side. X has to be greater than or equal to 2. That's our domain. All right, letter B, g of x equals natural log of 2 minus x. We'll do the same thing. We know that whatever's inside of here has to be greater than or equal to 0. So minus 2, negative x is greater than or equal to negative 2. Divide by negative 1. Now, just recall, when we divide by a negative number, it changes our sign. So it was greater than or equal to, now it's less than or equal to 2. And this is our domain. Letter C, h of x equals natural log of x squared. So we know that x squared has to be greater than or equal to 0. Square root both sides. X has to be greater than or equal to, technically plus or minus 0, but there's only such thing as 0. No positive or negative. Example 10. Students participating in a psychology experiment attended several lectures on a subject and were given an exam. Every month for a year after the exam, the students were retested to see how much of the material they remembered. The average scores for the group are given by the human memory model, this right here. T is the time in months. The graph of F is shown in this graph down here. Letter A, what was the average score on the original exam, so when T equals 0? All we're going to do here, plug that into our equation. F of 0 equals 75 minus 6 times the natural log of 0 plus 1. All right, natural log of 1 is just 0, so we'd have 75. That would be our original score. B, what was the average score at the end of T equals 2 months? So F of 2. All right, so wrapping up example 10 here. F of 2, again, we're just plugging in 2 into this equation, so 75 minus 6 times the natural log of 2 plus 1 equals. So again, we can plug this in. Since we already know what 2 plus 1 is, we're just going to plug it in as that. So 75 minus 6 times the natural log of 3, which is 68.4. Finally, letter C. So again, all we're doing is plugging in 6 this time. F of 6 equals 75 minus 6 times the natural log of 6 plus 1. So instead of plugging in 6 plus 1, I'd like to go 7. So 75 minus 6 times the natural log of 6 plus 1, which is 7. Oops. We get 63.3. That is the average score after 6 months. All right, so that is it for 3.1 and 3.2. I'll leave 3.3 up until next week, or we'll start that on next week. Yeah, hopefully if you need to go back and take a look at anything, definitely do so. You can slow this down if you want to, but yeah.